Annenberg Media.
I've told you before that science proceeds by proposing models and theories and then testing them by means of experiment. As a matter of fact, there's a point of view that says that the only way that science can make progress is by showing that theories are wrong. The argument goes like this. It's impossible to prove that a theory is right, no matter how many experiments agree with it. But if one single experiment disagrees with it, then the theory must be wrong. Well, that itself is a theory of knowledge which is wrong, because there are theories in science which are so well verified by experience that they become promoted to the status of fact. One example is the special theory of relativity. It's still called a theory for historical reasons, but it is, in reality, a simple engineering fact routinely used in the design of giant machines like nuclear particle accelerators, which always work perfectly. Another example of that sort of thing is the theory of evolution. These are called theories, but they are, in reality, among the best established facts in all of human knowledge. Well, our job today is to look into those facts and theories and models which underlie our understanding of the ultimate constituents of matter.
The long and winding road to the atom, from the atom itself to the nucleus, and on toward the ultimate constituents of matter, is designated by landmark theories and models. This model showed atoms streaking through space, bouncing off walls, and creating pressure in the process. This one illustrated how gas atoms interact and how they bind into liquids and solids. And this one gets right into atoms as they form molecules. Here's the atom, pictured as an ion with a loosely bound outer electron. That picture helped to explain the formation of metals. Still, the question is, why are there so many models? In other words, why doesn't someone just take a peek inside to see what an atom really looks like? Because to be seen, an object has to be large enough to reflect light. And the largest atom is 1,000 times smaller than a wavelength of light. In the literal sense, no atom will ever be seen. And to make matters very much worse, the nucleus is perhaps 100,000 times smaller than an atom. And yet, the job of this apparatus is to investigate not what an atom looks like, and not even what a nucleus looks like. Its job is to investigate the inner working parts of the protons and neutrons that are, themselves, the inner parts of the nucleus. To do that requires some very impressive machinery. That machinery exists here at the Fermi National Accelerator Laboratory near Chicago. However, to do the job also requires a new kind of mental machinery, a way of constructing and testing models that permit the mind's eye to see that which the real eye cannot. That machinery, it's called quantum mechanics, began with a model of the hydrogen atom proposed by Niels Bohr. In the Bohr model of the atom, the electron can exist only in certain orbits, orbits in which the electron circles the nucleus as if it were a planet going around the sun. Louis de Broglie suggested why. Electrons are waves that can exist only in orbits where they interfere constructively. And that can happen only if the circumference of the orbit is equal to the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any integer n times the wavelength. But brilliant as that idea was, it would not be the final word. Erwin Schrödinger, an Austrian physicist, understood that rather than being confined to an orbit, an electron matter wave could exist anywhere in 3-dimensional space. And he formulated the rules to describe such behavior. Those rules turned out to be novel and surprising, to say the least. However, and this is the test of any new model, they were also successful almost beyond expectation. It turned out that Schrödinger's new quantum mechanics could describe the hydrogen atom with the same precision and detail as the Bohr model before it. And then it could go far beyond. That is, it could account not only for the hydrogen atom, but for all the atoms of all the elements of the natural world. In other words, Schrödinger's quantum mechanics could explain nothing less than the periodic table of the elements. What then is the essential nature of this new quantum mechanics? And how is it different from the Bohr model? Even without going into all the details, much can be understood just by applying the Heisenberg uncertainty principle. For example, an electron has little mass and must therefore occupy a relatively large region of space. Conversely, the proton has so much mass that it needs to occupy virtually no space at all. The result is the quantum mechanical hydrogen atom, a tiny, massive nucleus surrounded by a cloud representing the electron. More precisely, the cloud represents the probable position of the electron. And that probability is largest near the nucleus and decreases rapidly farther away. However, the probability of finding the electron at a given distance from the nucleus increases at first, just because the volume of a shell at that distance increases. It reaches a maximum value as the shell expands, then decreases again as the electron cloud thins to almost nothing at large distances. Amazingly, the radius of the maximum is precisely equal to the radius of the first orbit of Niels Bohr's model of the hydrogen atom. And just as remarkable, its energy is exactly equal to that of the lowest energy state of the Bohr atom. So this is the picture, in the mind's eye of the modern physicist, of the lowest energy state of the simplest atom. The electron occupies a cloud instead of an orbit, but its most probable radius, and also its energy, is equal exactly to the values given by the Bohr model that came before it. But wherever in the universe it happens to be, the hydrogen atom is not always found in its lowest energy state. Like the Bohr model, the quantum atom has a different energy for each integer value of the number n. That energy results from the shape of the electron cloud. For n equals 1, called the ground state, the shape is a symmetric cloud, the the same in all directions. For n equals 2, there's a state with a double spherical cloud, one inside the other. But for the same value of n, and therefore the same energy, there's also a state with a donut-shaped cloud that almost suggests an orbit. This state has another integer, L equals 1, associated with it. N and L are called quantum numbers. And because the cloud isn't really an orbit, it's called an orbital. For example, there's another orbital with the same quantum numbers, n equals 2 and L equals 1. The same n means the same energy, and the same L means the same angular momentum. In classical mechanics, any orbit has a definite angular momentum. In quantum mechanics, certain orbitals have positive angular momenta, starting with the smallest allowed value, a little more than h bar. But the vertical component is exactly equal to h bar. That's for an orbital with L equals 1. However, though the vertical component is determined exactly, the actual direction of the angular momentum is quite uncertain. It can lie anywhere on the surface of this cone. And instead of being in orbit, the electron is in a donut-shaped orbital. So for n equals 2 and L equals 1, the electron orbital is a donut around a vertical axis. The angular momentum is anywhere on a cone around the same axis, and its component along the axis is exactly h bar. But that's not the only possibility. With the same n and L quantum numbers, the angular momentum could be horizontal. In fact, it could point anywhere in the horizontal plane. Then its vertical component is exactly 0, and its orbital isn't a donut, but two clouds, one up and one down along the axis. And finally, its angular momentum could tilt downward, producing a mirror image of the orbital of the up state. So with the same energy and angular momentum, n equals 2 and L equals 1, there are three distinct quantum states. They could be called up, middle, and down. But instead, a new quantum number, m, is given the values +1, 0, and -1. And of course, the story doesn't end there. For n equals 3, there's a whole new set of orbitals. Concentric spheres for L equals 0. Concentric donuts for L equals 1. And also double clouds up and down. These correspond again to m equals 1, 0, or -1. But now, L can also equal 2. These states come in a single donut version, a new variety with one donut up and another down, and another featuring a donut and two clouds. These correspond to m equals +2, +1, 0, -1, and -2. So here's the basic architecture of all the quantum states of the hydrogen atom. N can be any positive integer, starting with 1. And for each n, integer values of L are allowed from 0 up to n-1. Finally, for each L, m can go from +L to -L. This same basic structure will turn out to describe not only all the possible states of the hydrogen atom, it will also serve to explain the entire periodic table of all the chemical elements. The Greeks thought there were 4 basic elements: earth, air, water, and fire. As time passed, more and more elements were discovered, and by the 20th century, they numbered almost 100. Yet for all their diversity, all the elements owe their existence to a trinity of subatomic particles. neutrons, protons, and electrons. Like hydrogen, each element has many energy states. But for chemical properties, the most important is the lowest, the ground state. And the ground states of all elements follow the pattern of the excited states in the hydrogen atom. That state of affairs comes about because of two very peculiar quantum mechanical properties of the electron. One is the fact that the electron has spin. Not that it literally spins like a little Newtonian sphere, but it does have an intrinsic angular momentum, just as if it did. Its magnitude is a bit less than h bar, and its vertical component is exactly 1/2 h bar. And just like the angular momentum of an orbital, the spin angular momentum can be found with equal probability in any direction along a cone. That cone and its vertical projection can point up or it can point down. Those are the only possibilities. Nothing in between is allowed. The second quirk also has to do with the electron's quantum mechanical inner nature. No two electrons can ever have exactly the same quantum state. In other words, the probability of two electrons occupying the same state is exactly 0. That means no two electrons can ever have exactly the same quantum numbers in the same atom. But spin is itself a quantum number. So, if one electron has spin down and the other spin up, they can share the same orbital state. These, then, are the fundamental rules that govern the chemical elements, the stuff of life and everything else in the sea, on land, and in the heavens. The rules are these. Each atom can be thought of as an ion, the nucleus plus the inner electrons, with one final outer electron needed to complete it. That electron goes into the next, lowest energy available orbital and spin state. For example, 2 electrons are permitted in the n equals 1, L equals 0 orbital. The first one completes a hydrogen atom, and the second, with opposite spin, completes the atom of helium. This completes an energy level, making helium chemically inert. The n equals 2 shell of orbitals has room for 8 electrons. The first, with L equals 0, makes a lithium atom. The next, with opposite spin, makes beryllium. Now room must be made in the periodic table for atoms with orbital angular momentum, quantum number L equals 1. The first is boron, followed by carbon. These states have slightly different energies, even for the same n, and as each element is formed, it chooses the lowest energy state available. Following that rule, the shell fills up with nitrogen, oxygen, fluorine, and finally, the chemically inert noble gas called neon. According to the basic rules of atomic architecture, the n equals 3 shell will have room for 18 elements, starting with sodium, then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and the noble gas argon. But then a funny thing happens. Because of forces between electrons, the next lowest energy orbitals aren't the ones with L equals 2. Instead, a couple of slots in the n equals 4 shell get filled first, making potassium and calcium. Each element displayed in this way has chemical properties similar to the ones above it and below it in the periodic table. No matter how complex it may seem, the startling fact is that all the complexities of the natural chemical world have been reduced to 3 fundamental building blocks: the protons and neutrons of the atomic nucleus, and the electrons bound to the nucleus by the electric force, and the quantum mechanical rules of the game. 3,000 years ago, there were 4 elements: earth, air, fire, and water. Then there were 3: protons, neutrons, and electrons. 3 little words to explain the nature of the universe. And yet, they weren't enough. Not that physicists could or would ever discover anything wrong with protons, neutrons, and electrons, nor with the atoms as a whole, but rather that a new generation began to discover phenomena that, quite simply, protons, neutrons, and electrons could not explain. The longer scientists looked into the matter, the clearer it became. The number of elementary particles was not 3, but more, many, many more. And they could be produced and measured and studied in the great accelerators that, like this one, have become the tools and the monuments of modern physics. And as the number of known elementary particles increased, seemingly without limit, so did the need to organize what was known about them, to find patterns among their properties. In other words, what was needed was nothing less than a new kind of periodic table. But this one would be a periodic table not of atoms, but of the inner constituents of atoms. The neutron and the proton are close relatives of one another, and they belong to a larger family of 8 particles with similar properties. And each of those particles has an antiparticle with the same mass but opposite charge. Furthermore, for each particle and each antiparticle, there's another with similar properties but higher mass. And for each of those, yet another with still higher mass, and so on. So while one group of scientists, the experimentalists, labored at the great accelerators to find evidence of new elementary particles in the debris of collisions between the old ones, other scientists, the theorists, worked equally hard to find order in the increasing complexity and proliferation of particles. And in a striking example of history repeating itself, it was found that the patterns of the elementary particles, like the periodic table of the elements, could be explained if the particles, like the atoms themselves, had internal constituents. And like the constituents of the atom, there were 3 in number. They were called quarks. For example, each member of the family containing the neutron and proton is made up of 3 quarks. The large red shapes represent up quarks and have positive electric charge of 2/3, while the 2 kinds of smaller blue ones are called down quarks and strange quarks and have -1/3 of the elementary unit of charge. They combine together so that every complete particle has a charge of 1, 0, or -1 times the charge of an electron. Each quark also has spin, and they add together to give each particle as much quantum spin as an electron. The more massive particles, remember in modern physics more mass means more energy, have the same sets of quarks, but they're also in orbit, accounting for the extra energy. And so it goes, for this family and others. Elementary particles composed of even more elementary particles in combinations of quantum states. Like the proton, neutron, and electron, the 3 kinds of quarks called up, down, and strange may be only another chapter in the saga of atomic structure. Already, 3 more have been postulated. The latest are called charm, top, and bottom. And each of these types has an antiquark. Do they all really exist? With a brilliant model, a bit of luck, and a very big machine, perhaps they can be found just around the corner.
In the 16th century, when almost no one had heard of Copernicus, and even fewer believed what he had said, it was certainly believed by one person, an Italian monk by the name of Giordano Bruno. Bruno not only believed Copernicus' idea, he took it to its logical limit and believed that life would be found on other planets. I have here a picture, a photograph, of the Piazza Campo dei Fiori in Rome. And this statue in the middle of the piazza, in the center of Rome, is a statue of Giordano Bruno. Unfortunately, he won this honor the hard way. The statue stands at exactly the spot where he was burned to death at the stake for his beliefs in the year 1600. New knowledge, that is, knowledge contrary to a comfortable way of thinking, can be threatening to people, and they sometimes react violently to it. In this century, we have had a revolution almost as far-reaching as the one begun by Copernicus. We no longer believe that the universe will work out its destiny according to precise, deterministic, mechanical laws. That idea is the basis of all of Western thought since Isaac Newton, but according to quantum mechanics, it isn't true. Of course, most people are not yet aware of this discovery, just as in the 16th century, most people had never heard of Copernicus. But now you have been let in on that secret. Between the time of Copernicus and the time of Bruno, about 60 years passed. How long has passed since the invention of quantum mechanics? Well, it occurred in the 1920s. You figure it out. What you've been entrusted with is genuinely dangerous knowledge. Please be careful on your way home, and I'll see you next time.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.